Okay. Here we go. All right. Homework help for web assignment number 2. Hopefully this is not tricking you too much. I'm going to focus on making sure you have LOL diagrams so that you have a good setup, taking those snapshots. I truly believe that you're very, very well equipped when it comes to algebra. So that's not an issue. What I find to be the issue with energy is making those LOL diagrams, taking those correct snapshots before and after in any given problem. So let's take a look at this one. Child and sled combined mass go down a frictionless hill. Okay, so if I'm going to look at something going down a hill, right here we are at the top, and then we're coming down here to the bottom. So here's my first snapshot, here's my second snapshot. What's going on right there? Okay, and we want to know, it says that okay, I don't know about that Java update, why that's important, but, and hopefully it doesn't bother you and you don't really even see it. If the sled starts from rest, okay, so let's consider that up here the velocity then would be 0. We're looking for the velocity at the bottom of the hill. So if I'm doing an LOL diagram, what am I dealing with here? Well, I'm dealing, of course, with the sled, and I'm dealing with the earth because there's that whole height and potential energy thing going on. I do not have to worry about the ramp itself because there's no friction. So when I consider what kind of energy I'm dealing with, KE, UG, US, well, I don't have a spring. I'm not moving at the beginning according to the question. That means I have all potential energy at the beginning, gravitational potential energy. Since there's no friction, I'm not dealing with work, so I don't have to worry about anything happening here in the middle of my O, like my work in or work out. I'm also going to save myself some space and not put etherm in here because again, it's a frictionless surface. Not that I would want to account for it twice, but it is a frictionless surface. Again, no spring. But when I'm at the bottom of the hill, I don't have any potential energy because my height is 0, right? This is going to be the easiest spot to make my height 0. And then all of that potential energy, well, what happened? It started to move. So I can consider it all to be kinetic energy. What I can do then is write my formula from there. What I have at the beginning is equal to what I have at the end. And you should be able to expand from there and then, of course, eventually solve for velocity. Key things to look out for: check your metrics. Your mass is in kilograms. That works out pretty well. Your height is in meters. That's good too. Then, of course, when you're finding velocity, don't forget to take the square root when the time comes. So watch out for that as well. All right, let's move on to number 2. When catching a baseball, the catcher's glove moves by 11 centimeters. Motion of the ball, you're given a force, and you want to know work. Okay, so right away, we've got work being done, but let's consider what's going on. So here's this baseball, and it's moving. And then, of course, this is not going to look right. It's going to look like a cauliflower or maybe a turkey. I don't know, but that's supposed to be my catcher's mitt. Okay, so let's consider this ball is moving, and then this glove is going to exert a force this way over a distance this way. And you're going to catch the ball, right? You're going to give with the ball, and eventually the ball is not going to be moving anymore, right? Because you do work with the glove on the ball. So if you're considering an LOL diagram, what are we looking at? Well, now realistically, depending on how far the ball goes, it should drop, but we now have no way to work with that. So we're just going to say, nope, no potential energy here. We're dealing with all kinetic. It's all kinetic energy, right? In terms of a spring, I don't have a spring. Gloves are not springs. Oh, darn it, bad form, bad form. What did I do? I didn't do this. All right, so the ball is in my system, and then there's the glove. And I'm putting the glove outside of the system because the glove is doing work, and I'm drawing the arrow going out. Why? Because we're going to lose that energy. It's coming out of the system, and the ball is going to stop. So when I consider my kinetic energy at the end, we're assuming the ball doesn't really drop anywhere, maybe a little unrealistic, but again, we don't have any information to help with that, and it's not a spring. So what am I doing here? Well, I'm saying that all that kinetic energy equals the work. All right, well now let's take a look at what is actually happening in terms of the numbers in the question. So what am I being told? I'm being told 11 centimeters. All right, right away, Metrics alert. Change it to meters. Divide by 100. All right, you're given a force. This is my distance, right? And I'm being given a force in the question. And I know that work is force times distance. Oh, easy peasy. I just need to find the work. I don't really have to do anything with this. But what you could do, not that the question's asking you to, is you could actually work backward, figure out how fast the ball was going if you knew the mass of it, right? Luckily, I'm not going to ask you that today, so it's your lucky day. Makes it kind of easy. All right, let's move on to the last one. This one I answered the most questions about today during MOPS, and I just want to point out, what are we looking at? We're looking at my before shot. There's actually a really good example when we were doing pie graphs. There was one of these. All right, and so here, that's my first snapshot. We're compressing, and then the spring is no longer compressed, and let's say it goes all the way up in the air to there, to the peak of flight. Peak of flight means it's no longer moving. It's just about ready to come down. Okay, so let's consider what you're being given here. You're being given the mass of the block. You're being given the spring constant for the block, right? So mass of the block, spring constant of the block. You're given the compression on the block. And then it says it leaves the spring, travels upward vertically. How high does it rise? Let's do an LOL. All right, so LOL. We're ignoring friction. So really, what do we have? We have a spring, and we have the earth. And I made my zero, I made my O too small. This is let's see, spring, earth, block. I'm not trying to write the block outside the O. I just ran out of room. Oh well. Okay, so when I begin, I have all this spring energy, right? Because I'm compressing the spring. I'm going to make this my zero. Why? Because it makes the math easier, right? This is the same example. I mean, we have one like this when we did LOL diagrams where they then moved the bottom to the ceiling, and that made life a lot more difficult. So let's make this the height of 0, right? That way, from here to here is how high it goes. It makes your math so much easier. All right, so we've got spring potential energy there. We don't have any potential energy, and we also are not moving when the spring is compressed. All of that spring potential energy up here, well, it's not moving at the peak of flight. The spring is no longer compressed, but it is at height. So that gives us UG. When you set those equal to each other, you can then solve from there. A couple things that you want to just keep in mind. Again, watch out for metrics. Your centimeters, if you've got this in centimeters, it needs to be converted to meters. It is squared. Your mass needs to be in kilograms if it's not. In this case, it is. So it works out pretty easy. So hopefully you found those to be not all that tricky. And so you are ready to rock and roll when it comes to finishing up your homework. All right, guys, let me see if I can figure out where the recorder went. There it went. All right, I'll talk to you later.